Hello, this is a bit of a documentary, or a way for me to keep track of how I learn. I am taking a break from the AI world, because honestly I'm really not enjoying it. So I'm going to see if crafting interpreters is anything that I might find interesting. And I know the basics about all I know is that I needed to have Java and C installed. So take a look at the front matter, funny little dog, then acknowledgements for who's here. So open source repo of the book is pretty cool. Oh, yeah, that is actually pretty cool. Java C. You can even contribute. This guy works at Google, works in the Dart programming language, so it's pretty cool. Welcome. Beginning great adventure. Just explore plenty of room in your own creations. This is your first entry into the country. Welcome. So this is going to be my first entry. I got that right. Guided tour. Hiking boots, like that. Locks. The language, we're going to implement it twice. Okay. Introduction. Fairy tales are more than true, not because it tells that dragons exist. The dragons can be beaten. Okay. Book. Implementing interpreters, programming languages. Design a language worth implementing. First started getting into languages. It's a book I've been writing in my head for nearly a decade. Okay, step by step. So 2 complete interpreters for fully featured. I assume this is your first foray into languages. Definitely is. So cover each concept in line of code. That's pretty cool. In order to cram 2 full implementations inside this book. Doorstop. Lighter on theory than the others. Okay. I took a programming languages course in college, and the theory there was... I don't remember any of the theory. History and concepts behind it, get you familiar with the lingo. You'll find yourself in a cocktail party full of programming language researchers you'll fit in. Dude, that's probably happened to this guy. What's his name? Robert Nystrom? Yeah, it probably happened to him. He's probably been in this situation. That'd be pretty cool. You can probably have a really good conversation with these guys. Just getting language up and running. Theory isn't important, but we can just go find another book. You can believe how much some of them can drink. Oh yeah, it literally says it right here. Okay. Being able to reason precisely and formulate about syntax is a vital skill working on a language. Personally, I learn best by doing. Yeah, I agree. I learn best by doing too, so that's good. Particularly require rigorous formal reasoning. Hacking on the type system is the same feeling as proving a theorem in mathematics. I mean, if you ever program in like Haskell, then you're basically just doing math. Let's be honest. And I'm also going to be honest. I did not fully grasp that much as traditional imperative programming. Yeah, so look, Haskell, fucking Haskell. I don't even know what this is. What is this? Curd-Howey correspondence? Oh god. Love theory. Love theory. Yeah, I don't think I want to understand the theory until I actually see it done first. And even then connecting it's kind of hard. It took me a while to understand just how to visually connect you see a neural network displayed visually and it's just a graph. It took me forever to connect that to like, it's just a bunch of math equations chained together. This is a pretty good book. I read the first couple of chapters of it. I just didn't get into it all the way. Yeah, it's ebook, $29. there are definitely not places on the internet where you can get this for free. Absolutely not. Every compiler book, I don't know what it is about programming languages that causes such existential doubt. Ornithology books? That is a word about birds, probably. That is probably a word about birds. Yep. Wait, I wanted to see that picture. Oh my god. Oh yeah. Oh hey. Oh yeah. Okay, I'm getting very distracted. Designers of the world's widely used languages could fit into a Volkswagen bus, even without putting the top camper up. If joining that elite group was the only reason to learn languages, it would be hard to justify. Fortunately, it isn't. Yeah. Little languages are everywhere. For every successful general-purpose programming language, there are thousands of successful niche ones. We used to call them little languages, but inflation in the jargon economy led to the name domain-specific languages. These are pigeons. Tailor built to a specific task. Yeah. I mean, I try to get into Emacs, I just never could. Awk is a language? I did not know that. That's pretty cool. Are these even languages, or are these Markdown languages? Like, is YAML not just Markdown? SQL? Well, they are languages. They're not necessarily programming languages, right? They're just languages. So, you know, that makes sense. Yeah, like these are definitely these are languages. Every large software project needs a handful of these. True. There's a good chance you find yourself needing to whip up a parser or other tool. There isn't an existing library for that fits your needs. Well, yeah, that would be nice. I was experimenting with file data format, VDF, and it's kind of a pain to parse. Well, okay, it doesn't seem like it'd be too bad to parse. It's very similar to JSON, but not exactly. So I ended up Python project. I just used this VDF, and it worked out pretty well. I heard this book did a little bit of compilers as well. So, okay, challenges. That's cool. Reusing existing implementation and really end up needing to debug and maintain it and poke around in its guts. Languages are great exercise. Long distance runners, sometimes trained at weights or high altitudes. Yeah. They don't better themselves. They're good. Yep. Implementing a language is a real test of programming skill. This guy is doing a good job of appealing to me so far. The code is complex and performance critical. Recursion, dynamic arrays, trees, graphs, and hash tables. I like the idea of hash tables, but do I really understand them right here? Absolutely not. I don't understand hash tables at all. Well, after we craft our own from scratch, I guarantee you will. Alright. Okay, I like that. I like that a lot. And I intend to show you that an interpreter isn't as daunting as you might believe. Implementing one is still a challenge. I believe that too. Rise to it and you will come away a stronger programmer. I like that. Smart about how you use data structures and algorithms in your day job. I like that too. Because I'm going to be honest with you, I haven't implemented a linked list since college. And that implementation was absolute dog shit. Implementation was so bad. So, I'm just gonna learn how to do it now. Last reason for me, hard to admit, so close to my heart. Ever since I've been programming as a kid, I felt there was something magical about languages. When I first tapped out BASIC, one key at a time, I couldn't conceive how BASIC itself was made. Yeah, well, the big thing about programming languages for me is assembly, and I don't know how much I want to get into that, but I think it's nothing to avoid, and my big issue with assembly was that it felt like it had too many side effects. Like, you run this command and then command. Is anyone in command? you type this instruction and then it changes this register to show that a bit has flipped or whatever, and some other register that represents like overflow or something. And that kind of bothered me. I didn't understand. I didn't go step by step. I didn't like memorizing what each of the instructions did. It just didn't seem very appealing to me. So I think in this I'll probably have to get into it a little bit, but this book doesn't seem like it has any assembly in it. So this is a good first step, I think. When I first tapped out, later the mixture of awe and terror on my college friend's face when talking about their compilers class enough to convince me language hackers were a different breed of human. Some sort of wizards granted privileged access to it. Later, the mixture of awe and terror on my college friend's face when talking about their compilers class was enough to convince me that language hackers were a different breed of human. Yeah, we didn't even make like a programming language in my compilers class. It wasn't even a compilers class. It was a programming languages and translators class. We didn't even do compilers. We didn't even make a compiler. We made a lexer. And one of the assignments was just go and use some GCC commands to output multiple files, and then do some regex yourself, and then compile it. And it was really easy. Regex is one of the first things I learned, and I'm so glad I did. It was so easy. It didn't feel difficult. I didn't have anything to show off. Right? I made a recursive descent parser in Python, and it didn't even work fully, but I still got 100% on the assignment. Like, okay. I didn't feel like I learned anything in that class. Made up keywords in my school notebook. Damn, this guy's been really into languages for a while. That's pretty cool. No wonder he works at Google working on Dart. That's crazy. Gather my own little interpreters. We learned, of course, that there is no magic at all. It's just code, and the people who hack on languages are just people. Aren't we all? Aren't we all just people? A few techniques you don't often encounter outside of languages. Some parts are a little difficult, but not more difficult than other obstacles you've overcome. My hope is that if you felt intimidated by languages, which I definitely have, the book helps you overcome that fear. Maybe I'll just leave you a tiny bit braver than you were before. Yeah, I'd like that. And who knows, maybe we'll make the next great language. Someone has to. Honestly, I was fantasizing about working on the Rust compiler. That seems like it could be fun. I really respect Rust as a language, and anybody who can program in it. It's not easy to learn, and it's coming from an object-oriented stance. Getting into that was difficult. I learned Haskell before I learned Rust, and that was honestly a really, really good thing to have. So if you want to go learn Rust, go spend 2 months dicking around in Haskell. That was definitely worth it. And I'm still not even good at Rust. I'm still not good at Rust. It's been a couple months since I've touched the language. So if I go back to it, I'm going to be super, rusty. Okay, this book is broken into 3 parts. You're reading the first one now. It's a couple of chapters to get you oriented. Teach you some of the lingo that language hackers use and introduce you to locks. Language will be implementing. This guy's probably been thinking about locks for so long. Shit. Okay. Each of the other 2 parts build Part 2. Each of the 2 parts build 1 complete locks interpreter. Within those parts, each chapter is structured the same way. The chapter takes a single language feature, teaches you the concepts behind it, and walks you through the implementation. It could be a trial and error on my part, but I managed to carve up the 2 interpreters into chapter-sized chunks that build on the previous chapters but require nothing from later ones. Okay. For the very first chapter, you'll have a working program you can run and play with. With each passing chapter, it grows increasingly full-featured until you eventually have a complete language. Aside from copious... I don't know this word.
Scintillating.
You guys could probably hear that. I don't have my speaker on right now, so I cannot hear that. Scintillating. Animated, brilliant, or highly skilled. That is not going to stay in the recesses of my brain for very long. Chapters have few other delightful facets. The code. Talking about crafting interpreters. It contains real code. Beautiful. Every single line of code is included. Each of it tells you where to insert in your overgoing implementation. Language books use tools like Lex and Yak that automatically generate some of the source files from implementation from some high-level description. Ensure that there are no dark corners where magic and confusion can hide. I like that. There's always a reason in an interpreter, in a programming language. Because different constraints from the real world, so the coding style here might always reflect the best way to write maintainable production software. That's fine. This guy probably wrote it for fun, and he works at Dart at Google, so I'd say even in his fun time, he still has the muscle memory of a professional maintainable code base, so I trust this guy. Cavalier, about emitting private. Declaring a global variable. Give the code easier on your eyes. The pages here aren't as wide as your IDE, and every character counts. Also, the code doesn't have many comments. That's because each handful of lines is surrounded by several paragraphs of honest-to-God prose explaining it. When you write a book accompanying your program, you're welcome to omit comments too. Otherwise, you should probably use the comments a little more than I do. I agree. I was actually reading through config.app. Go here. I was reading through how this worked right here. Right, random little TF2 optimization software right here. One of my favorite games. You just see it out in the wild. Like, you go to the debugger, you go to utils, and you look at the code that Mastercoms wrote, and she commented it, as I see no comments. Right, here we go. Like, some of this code is commented, and it's not like ChatGPT code like that I sometimes use. So, yeah, this is pretty cool. See it in the wild. Like, people just use comments, and it's really helpful. Especially when I'm reading through something new and I don't want to sit down and decipher, like, what does this if statement do? It just tells me right there. And that's why comments are cool, because it helps people immediately understand what's going on rather than, go look at the code. One of my, I used to work at a research lab back at university, and my direct coworker said that he didn't comment its code because he writes it well enough to where it should just be understandable. And let's just say I still think about that when I write my code. So I try to comment. Am I the best at it? Absolutely not. Line of code and teaches you what it means. It does not describe the machinery needed to compile and run the interpreter. Soon you can slap together a makefile. Yeah. Those kind of instructions get out of date quickly, and I want this book to age like XO Brandy, not Backyard Hooch. This book contains literally every line of code needed for the implementation. The snippets are also quite precise. Also, because I try to keep the program in a runnable state, even when major features are missing. Sometimes you have temporary code that gets replaced in later snippets. The snippets, all the bell and whistles looks like this. Okay, all the bells and whistles in this one. Scanner.java. If is digit number. Else. Expected character. Unexpected character. Alright, I like that. Case statement. Switch statement. Yeah. In the center, you have the new code to add. I'd have a few faded out lines above or below to show where it goes in the existing surrounding code. The new code, so this is new code. A few faded out lines to show where it goes in the existing code. That's smart. If the blurb says replace lines, there's some existing code between the faded lines that you need to remove and replace the new snippet. Replace one line right here. The sides. The sides contain biographical sketches, historical background references to related topics, and suggestions to other areas to explore. There's nothing you need to know them, understand later parts, so you can skip to them if you want. Well, some of the sides do. At least most of them are just dumb jokes and amateurish drawings. Did he draw this himself? He might have drawn it himself. Seems like he was having fun too. Fit right in here. I like this. I like this. I like this. They really spelled yak like that. Each chapter ends with a few exercises. Unlike textbook problem sets, which tend to review material you've already covered, they tend to help you learn more than what's in the chapter. Okay. That's good. They force you to step off the guided path and explore on your own. It will make you research other languages, figure out how to implement features, or otherwise get you out of your comfort zone. Research other languages. Okay. That's scary. But that'll be okay. The challenges often ask you to make changes to the interpreter you're building. You want to implement those on a copy of your code. The later chapters assume your interpreter is in a pristine, unchallenged state. That makes sense. It's our book. Most programming language books are strictly programming language implementation books. They rarely discuss how one might happen to design the language being implemented. Implementation is fun because it is so precisely defined. We programmers seem to have an affinity for those things that are black and white, ones and zeros. So precisely defined. Yeah, I agree with this statement. Personally, I think the world needs only so many implementations of Fortran 77. How many different implementations of Fortran 7 are there? Cool. At some point, you find yourself designing a new language. When you start playing that game, the softer human side of the equation becomes paramount. Things like features which are easy to learn, how to balance innovation, and familiar with syntax is more readable, and to whom. All that stuff profoundly affects the success of your new language. I want your language to succeed, so in some chapters I end with a design note, a little essay on some corner of the human aspect of programming languages. Hard code assumptions about the width of a punch card into its grammar. Is this statement a reference to something in the programming languages world? Don't design your programming language with arbitrary or outdated limitations inherited from obsolete technology. ChatGPT is spitting facts here. Limit of 80 characters per line. COBOL has an 80 character per line limit. That's still in use today. Yeah. Okay. Thank you, ChatGPT. That was a pretty cool history. That was a pretty cool history lesson right there. JLocks in Java focuses on concepts. The simplest, cleanest code can do correctly input the semantics of the language. Let's get us comfortable with the basic technique. I also have Java installed, so that will be okay. I don't know what the difference is between these two. I kind of just installed the development version, so, okay. Java is a great language for this. It's high level enough that we don't get overwhelmed by fiddly implementation details. It's pretty explicit. Like attributed languages, there tends to be less complex machinery hiding under the hood. We've got static types to see what data structures you're working with. I enjoy static types. I've been mainly a Python programmer. And the dynamic typing it's nice. Honestly, it's nice. It has its benefits. But I like the readability that comes with static typing. And honestly, it kind of makes it easier to logic through it too. So, just static typing languages have kind of been difficult for me, and I think it's time to maybe not. Time to just go and learn these. Specifically object-oriented, the paradigm swept, the 90s now with the dominant way of thinking. Yep, odds are you're already used to organizing code and classes and methods. Honestly, I'm not the best at doing that. I know how to program, but I typically only write small scripts. I haven't really done anything large, so this book can help me understand how to do object-oriented programming. While academic language folks sometimes look down on object-oriented languages. The reality is that we're widely used. GCC LVM are written in, I didn't even know GCC was written in C++. So most JavaScript VMs, multiple object-oriented languages are ubiquitous, and tools for Tools and compilers for a language are often written in the same languages. Yeah, I know about that. Like, isn't GHC written in? It's written in Haskell, right? Yep. Haskell compiler. And GitLab. Yeah. Glorious Glasgow. Glorious. Oh my god. Yeah, mostly Haskell. There's some C, but it's mostly Haskell. I don't know what the Rust compiler is called, so let's see what the Rust compiler repository. Rust. Written mostly in Rust. Small amount of C. Oh. Probably gotta sign in to look at the code, so I'll probably end up doing that later. Or maybe honestly I probably won't end up doing it later. Java is hugely popular. Good chance you already know it. So there's less for you to learn to get going in the book. If you aren't that familiar with Java, don't freak out. I try to stick to a fairly minimal subset of it. Use a diamond operator from Java 7. I don't even know what the diamond operator does. Java 7. Oh shit, wait, is this just type declaration? Okay, hold on. So, that was the right-hand side of the event to be defined as a true generic instance. The same type parameters on the left side, so generics. Not legal, since the right side is generic. This is not giving me, that is not concise. What is... Okay, so that is how it works. Cool, alright, I like that. I barely understand generics, by the way, so maybe this would be something that is cool. If you know another object like C#, C++, you can muddle through. I used C++ in college, so this won't be too bad. Although it has been many, many, many years. Okay, by the end of part 2, I have a simple readable implementation. Oh, cool. It's not very fast, but it's correct. However, we're only able to accomplish that by building on the Java's virtual machine own runtime facilities. We want to learn how Java itself implements those things. I wonder if he's going to cover that in the book. Or if that's just understanding the thought process behind how Java does it. I really hope he does cover at least a little bit of it in the book. The compiler reads files in one language, translates them, and outputs them into another language. You can implement a compiler in any language, including the same language itself, self-hosting. You can't compile your compiler using itself yet, but if you have another compiler for your language written in some other language, you can use that one to compile your compiler once. Now you can use that compiled version of your own compiler to compile future versions of itself, and you can discard the original one compiled from the other compiler. This is called bootstrapping. From the images of pulling from the image of pulling yourself up by your own bootstraps. Okay, I'm a fan of this. The second interpreter. So in the next part, we start all over again, but this time in C. Shit. All the way down to the bytes in memory and the code flowing through the CPU. Fuck. Yeah, this is definitely going to be a second part 2. Because this is what I am not comfortable with at all. This I do not understand. So, yeah. A big reason that we're using C is I can show you things C is particularly good at. But that does mean you'll need to be pretty comfortable with it. You don't have to be a reincarnation of Dennis Ritchie. I feel like this name is important. I should know who this is. Co-inventor of Unix and the C programming language. This looks like AI. Remembering? Damn, he died? No shot, he died. He was in Bell Labs too. Died. Damn. Wait, this picture is from the year he died? The fuck did he die from? I kind of don't want to think about that. If you aren't there yet, pick an introductory book on C and chew through it, then come back here when you're done. In return, you'll come across this book, An Even Stronger C Programmer. That's useful given how many language implementations are written in C. Lua, C Python, Ruby's, MRI, to name a few. RC interpreter clocks. Yeah. We're forced to implement ourselves all of the things Java gives for free. We'll write our own dynamic array and hash tables. Dynamic array and hash table. Okay, I've done that in C++ before. Decide how objects are represented in memory and build a garbage collector to reclaim them. I've never built a garbage collector before, so that's going to be cool. Pronounce the names like C-locks. The name like C-locks. But you can say clocks or clock. Or you pronounce the X like the Greeks do if it makes you happy. Oh, okay, I get it. Latech, clock. Silly. Java implementation was focused on being correct. Now that we have that down, okay. The C interpreter will contain a compiler that translates locks to an efficient bytecode representation. Don't worry, I'll get into what that means soon, which it then executes. This is the same technique used by implementations of Lua, Python, Ruby, PHP, many other successful languages. We're going to try our hand at benchmarking and optimization. By the end, we'll have a robust, accurate, fast interpreter for our language, able to keep up with other professional caliber implementations out there. Not bad for one book and a few thousand lines of code. I think this could be fun. I heard about this book because I have the TV on behind me, and CodeScope created one where he implemented this book back in 2022 in Rust. And I thought, oh, well, I want to go and learn Rust and see how programming languages and compilers work in Rust. But he starts reading through chapter 1, or I guess chapter 3 about scanning and stuff. And it's clear he knows way more than I do about this. So I decided that if this guy who knows more is doing it in Rust, then I should probably just go and learn, like, how all of this works to begin with. So that's what this is. I have basic experience with data structures and interpreters. I don't have anything with compilers. So that's where I am. That's what this is tailored to. I'm probably going to edit this a little bit and upload it eventually. And I'll see if it's been pretty fun. Sort of a digital log per se. And I know that people are going to watch this if I upload it to YouTube, which is kind of scary, but I think it'll be okay. So let's look at the challenges, shall we? 6 domain-specific languages used in a little system I cobbled together to write and publish this book. This is editing Rowan and post. I basically just spent the next, 5-10 minutes looking through the repo and trying to find all these little languages that I used. And I totally cut it out, but here is what I saw, and the answers totally say something different. I'm going to look at that later. Get Hello World running in a program. So I need to... I'll save this for now. Project locks. JDK. Detected JDKs. USR lib. Java 24. That system.out.println. Hello world. That was annoying. And that's all it turned out I needed to do was point it to a different file. Okay. That was obnoxious. It's done now. Hello program. Set up whatever make files or IDE projects you need to get it working. Like a debugger, get comfortable with and step through your program as it runs. Do the same thing for C. Get some practice with pointers. Oh no, I haven't done C in so long. Define a doubly linked list of heap allocated strings. Write functions to insert, find, and delete items from it. Test them. Fuck. He said, go and do it. This is the exact thing on my, this is the exact project, this is the exact homework assignment that I totally fucked up. Going to find a doubly linked list and see, have fun. Have fun, have fun. So, what's next? And use your nice little visual. You got null right here. Then the first element of the list points to null, then it stores a value, and then has a pointer to the next one, which then has a previous, so we're just going to make a class. It has a value, then next, and then first, and then, yeah, that'll be the linked list. We're going to need to count our way up through it too, which is going to be fun. Yep, it has been a while since I have programmed in C. Hello, world. Hello, world. I haven't done this in a long time. Okay, I will go and learn CMake if I need to. But might not need it, honestly. Then I should probably init. Probably create a get repo for this. Then just commit. And I'll leave everything in the idea folder. No idea why that's red. Okay, so it ran one more time for good measure. Hell yeah. Now I need to make a doubly linked list, and I haven't done that in so long. Okay. So I'm setting up the environment. I'm going to pause the recording and go and get some fresh fucking air, and I'll come back and implement this doubly linked list. It's been a while since I've done it and he wants it in C. And I'm just going to use a struct. And give it a forward-facing pointer, a backwards-facing pointer. If I want to delete out an index, then implement the most jank append ever. Make sure you can insert, find, and delete items from it. Yeah, I'm just going to make the most scuffed linked list code ever. And it's gonna be great. I'll be back later. Totally aligned because my computer is gonna lock, and then the scene's gonna be messed up, and I gotta close and open OBS again. So I'm just gonna stop recording, and then I will. I'll just come back. Okay, welcome back to my video vlog series. So this is supposed to be in C. I'm gonna try to avoid classes and I'll just use structs instead. And that should be okay. I know C doesn't have any inheritance, so I won't do any more of that, but let's create our struct node. It has been a while since I've created. We're going in editing again. I ended up spending the next 30 minutes of that recording fumbling around with linked lists, and it didn't really go too well. So in the next clip, I'm going to be watching a YouTube video, and I'll mention the name in there, and I'll post the YouTube video I watched in the comments or in the description. So just keep that in mind, that it's just going to be me watching a video on how to make a linked list. And something else is that the linked list implementation had memory leaks in it, so I go and decide to fix that. I don't exactly follow the book instructions either. I totally do an int, and I'm not sure if I make a delete node function, but at this point, I kind of just want to move on with the book. So, yeah, it'll just be me programming along with one of these other, with the YouTube video. Bye-bye. Hello, everybody. It's the next day. YouTube documentary. Basically, I cobbled this together, and I got stuck. Learn doing linked lists, and the book says go learn how to do linked lists. And admittedly, yesterday I was a little touchy on my pointers, and I forgot. Honest to God, I forgot like what a reference is, and I forgot like what the dereference operator does. I didn't have it concrete in the back of my mind. Like, sure, I knew I had to do something with memory addresses, but I didn't have it concrete, right? So now, address of this dereferences a pointer, and that makes sense. And then this, I know the arrow also has something to do with referencing the value inside of a struct if it's inside of a pointer. So it's a shortcut. I know this is a shortcut. So I decided to take a step back and go and watch Jacob Sorber's Understanding. Here, let me see if I can't move it over to... I took a step back and watched most of this video, but I'm just going to be walking through it. I'm just going to be programming along with him, and then we'll see. And he even has a doubly linked list as well. So I'm going to do the linked list first, and then go and look at his doubly linked list video too. So that will be something to do today, and I'm just going to get rid of all of this. Actually, good practices pre-Jacob. In case I want to go back. Sorber video. There. Boom. Easy. Okay, so basically now just bye-bye. He has a very similar struct to me, but I like how he I like his naming conventions in the video. So I'm just gonna start playing it.
Hey everybody, welcome.
If you like, I found out about Invidious through like Privacy Brain, but honestly I just use Invidious now because I don't have to install an extension and it has an ad blocker built in. It just works. You know, if there's one question that I have, it's that, sure, an int, depending on your system, is either 2 bytes or 4 bytes, but you also have longs and shorts. And I never really understood when it's better to use one over the other. Here we go. See Eric's answer. Int is set to the natural size. Yep. Yeah, you can conserve memory, of course, but I guess maybe if you're on a microcontroller or something. Yeah, conserving memory is critical. Yeah, okay, so it's just for memory.
I'm just going to declare them as local variables for now.
Yep.
We're probably going to change that later, and we'll set their values, and then let's link them up into a list. And just for kicks, we'll make the third one the front of the list, followed by the second, followed by the first. I can put them in any order. This is just...
Oh, I don't care about this. Value 3 dot n value equals 3. So we'll keep this up. So, and then I'm going to follow this length nodes.
This is just completely arbitrary. And we'll make the head point to the address of N3. That's what the ampersand means, if you haven't seen it yet. Then we set each node's next pointer to the address of the next node. And
oh, you defined struct node a pointer towards head. Okay, so the head node is not going to do anything. Yeah, it's just not going to do anything. Set M3 and next. equals a reference to N2, so whatever the code is pointing to. And then in one.next, I'm gonna say it's gonna be null pointer.
And we need to know where the list stops, so we'll set the next pointer for the last node to be
Yeah. Just stop.
null. And now we have a list, and let's add a function that prints out a linked list if we pass in a head. And this is easy. We're gonna
Declaration of someone. Yeah. Okay. True. It can't be joined. Void print list struct node colon head. So now I'm going to try to do this myself before I will look at the code that Jacob Sorber is going to write. And we'll see how this goes. So we're given head. So I guess I could do this recursively. If I want to print them in order, then I should do printf. Okay, yeah. Don't know if that's going to work or not. Head can be made pointer to const. And then let's do print list head and next. It doesn't like that. Infinite recursion. Yeah. Yeah. So if it's not equal to null, then do that. Boom. Beautiful. I don't really see the issue with that, but okay. I need to actually call the function. Print list head. Do I need to pass this as a reference? Oh, wait, no, it's already a pointer. Then that lines up right there. Beautiful. Okay, 3, 2, 1. Yeah, that's it. Okay, let's see how he does it.
We're going to pass in the head pointer. That tells us where to start. And then we're just going to declare a temporary pointer. I'll call it temporary, so we don't forget that it's temporary, and set it to start at the head pointer. Then we just follow the links. As long as the temporary pointer isn't null yet.
Oh, okay, so he does it iteratively. So struct node temp, set that equal to the head, and then while temporary is not equal to null, just print it. Then I like this. Like it, he did that in the video, and then print that out. Beautiful.
Meaning we haven't hit the end yet. We're going to print out the value of the node that temporary points to, and then we'll move temporary to point to the next node in the list. That pointer is just
oh, yeah, totally forgot. Temp equals temp next.
Bouncing along down the list, printing each node that it finds. And finally we hit the end, and I print a new line just for the sake of pretty formatting. Okay, so now let's call our function down in main with the list we created. We compile it, and we run it, and it works. Okay, now this is a good time.
Okay, so this is my implementation. I wonder why recursion is a problem. Jacob Sorber's implementation.
Time to stop and play around a bit, because we can quickly reorder our list, and we compile it and run it, and...
Alright, yeah, I'm going to reorder my list.
Reference to N1, set this one to null pointer, this one to N3, and this one to reference to N1, the address of N1. Wait, N2. Does that make sense? N1, N2, head points N1, N1 points N2, 2 points N3, yeah. That works just a little strange out of order, but...
That should be okay.
And look, now it prints out the new ordering. Okay, and we can add a new node to the list, and let's insert it in the middle.
First 3 nodes. Okay, so now I'm going to add another node. So struct node in4. Then set that equal to 4 in4 dot next. He's setting it to a reference, the address
Of course, and if we compile it and run it, you notice that the node is there, right there in the middle, and I can remove the first node by just moving.
Wait, hold on, what?
Notice that it's inserted in the middle, of course, and if we compile it and run...
Into next equals reference to N4. Does it, wait, does this actually work how I think it does? 1, 2, 3, 4, 1, 2, 4, 3. Okay, hold on. We're gonna run this chain down through my head. So, M1 is set to the reference of N2, and then N2 and next set to the reference of N3, right there. Right, and then N2 gets set to N4, and then, oh, yep, that makes sense.
Run it.
Cool. You notice that the node is there, right there in the middle, and I can remove the first node by just moving the head pointer down a link. So hopefully you're following along, make sure this all makes.
Yeah, so you see what he did here? He moved the head down. And then that will get rid of that. I should get rid of the 1 right there. Yep. And then if I delete this, and then let's say if I set N4 dot M next to null pointer, then it should only be 1 and 2. 1, 2, 4. My thought process was a little bit wrong there. If I set N2 next to null pointer, then that would change it. So if I do that, then there you go. Yeah, N4 would still have the value in it, it's just the next one wouldn't have anything in it. That makes sense. Yeah. Just overthinking some things. So, you made N1 a pointer. Then down here, you did N1 malloc, the size of struct node. Okay, and then that is invalid because now it's a pointer and we need to access something inside of a pointer. And then I'm going to go down here and change that to, and I wonder what this is going to complain to. Implicitly converted into pointer type of struct node. Okay, so if I want to dereference twice now, the address at the address of, oh, that was it. Declaration and assignment can be joined. Alright, so, yeah.
Allocated nodes and 1 on the heap, but this is getting a bit messy, so let's change.
Let's see, so he got rid of the N4 right here. Let's see what happens if I just comment that out and run, oh, that's a compilation error. Label N1 used but not defined. What happens if I leave the implicit? Nope. Assignment to struct node star from incompatible pointer type struct node double reference. Okay. Let's see. If I do this, what's the error here? Label N1 used but not defined. This is strange. Well, that would make sense. Because in the video right here, it's just straight to N1. Let's look at these types so I make sure I have this. Head is a pointer of node, and that is also a pointer. So that lines up. It's a memory leak. That is one of the big struggles I have with C and C++, is that I don't know how to fix a memory leak. So when I see it, I think, oh well, which is not good practice. So how do I go about, at the end of the program, I probably need to free that N1 pointer up. And then since that's a pointer on this is on the heap, so since that's a pointer on the heap, then it'll probably be okay. I could probably make a recursive function, make function for this later. Then, yeah, that'll be okay for now. Let's run this, make sure it's cool. Yep, 1, 2, 4, 3, looking good. So we're gonna want to struct node.
New node and take an integer argument. And inside the function, we will allocate a new node using malloc,
node.
and we're going to set its value. And just for sanity's sake, let's initialize the next pointer to be null, and return the pointer to the new node.
Alright, he is speedrunning in that video, which is okay. I can pause. So here, go like this. We set the, let me make this result like he does. result in value equals value, result index equals null, return result. Wish there was a way to change this. I like null pointer. I agree with that. Value can be made const. Yep. Then this is optional.
Okay, now we can change up the main function a bit. Let's remove our statically allocated nodes and just use one pointer. And our new function will allocate new nodes and add them to the front of the list.
Okay. All right. Pre-use of create node. In case I need to go back. Okay. In case I need to go back. All right. Goodbye. Ring bling. Turns a pointer. Ring bling. Then okay. Let's create node 1. I need to actually declare these. TMP. Beautiful. This is going to be memory leak. Yep. Okay. Head equals TMP. Memory leaking still? Yep. TMP equals create node 2. TMP pointing towards next equals head. Okay. Do not understand. Head equals TMP. Okay, hold on. So what's going on here? Then we're gonna need to free. We're gonna need to free TMP, and that stops the memory leak, according to JetBrains at least. So TMP creates a node, and then head gets set equal to TMP. Okay, so the head is now 1, and then TMP gets reset to a new one. TMP mnext gets set to the current pointer to head, and then head gets set to the new TMP. So that means 2 was printed before 1? Yeah, okay. That makes sense.
And we can compile and run, and you see
They even created more nodes. Okay, well, I'm just gonna do this. And that should be 1, 2, 3. 3, 2, 1.
see we still have a
4 int n equals 0 n is less than 25 and plus. Then just gotta copy one of these through blocks. Boom, 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 boom. Okay, yeah. So that works. Works. Head might not be initialized.
numbers from 0 to 24.
Yeah, he does it. He initializes it right here. Okay, that makes sense.
And we compile it, and it runs, and
Yeah,
notice that the
so it's
numbers
gonna
are in
return
reverse
0.
order. Why? Well, it's because I added each number to the front of the list each time. So the last number I added, that 24, is at the front of the list. It's the last one that...
If I free, what happens if I free unused? What happens if I free something that's unused? Okay, it does nothing. Cool.
that got added. And this again is a good place to stop and make sure that everything makes sense. And I know that some of you up to this point in your education have wondered what use pointers are anyway other than frustrating students. Well, this is one place where pointers are a huge benefit, and I hope you're starting to see that. They make this whole linking the nodes together thing possible, and they also allow us to keep track of all of these nodes without having variables for each of them.
Man, I should have just put the
Because
time
they're all
and
linked
effort into
together,
learning
so they're
this,
just
rather than
we
trying
keep
to
track
speed
of
through
them
it in college.
indirectly through the pointer linkages.
Would've been
Okay,
so
so
much
where do
better.
we go from here? Well, one thing that most people do is to make some functions for common things that you want to do with your list. And for this example, I want to make a few. First, let's make a function that's going to do what we've been doing all along and add a node to the head of the list.
Okay, yep, this is something that I was struggling with. And my in my
the
implementation.
list. So now I could do this a few ways. For starters, let's just take two arguments, the head of the list and a pointer to the new node that I want to add.
Then struct node to insert.
And we'll do just what we did in our loop. We point the new node's next pointer to head, and then we return the address of the new node, which will become our new head pointer. And now with this function, now down in our loop,
Well, what? Oh, yeah, okay. Duh, that makes sense. Yeah.
we can simplify things a bit. Keep in mind that our function doesn't change the head. So we actually have to set the head to the new pointer that the function returns, but that's still pretty simple. So let's compile it, and okay, so that works. Now let's say that I don't want to have to assign the new head myself. We can change things a little.
Maybe null. This is why I'm just going to use Rust. Because it'll error if it does shit like that. Maybe null when calling from function main. Like, fuck. Actually, fuck.
A little bit like this.
Okay.
And what I want to do is to pass in a pointer to a pointer, and this allows us to change the head pointer, and we can now update it inside the function. And
Okay. I missed this.
that simplifies pointer myself. So let's compile it and set the head to the new pointer that the function returns, but that's still pretty simple. So let's compile it, and okay, so that works. Now let's say that I don't want to have to assign the new head myself. We can change things a little bit like this. And what I want to do is to pass in a pointer to a pointer, and this allows us to change the head pointer, and we can now update it inside the function. And that simplifies main a bit more.
Head
And so now if we compile it and run it, it still works. Okay, so let's add some more.
Oh, failed? Oh, yeah. I gotta pass a... I have to pass a reference... Hold on. I have to pass a reference. I have to pass the address of the head pointer. This is a double pointer.
More functions. Let's make a function that finds a node.
Okay. So, I want to see what this variable looks like inside. Debug this. Let's see. Okay, step over. So the pointer
Node. So let's add some more functions.
don't do that anymore. Okay, yeah, that brings it out of that, which makes sense. Because we're setting head in there. So we're setting the node to insert, the next to a reference to head. And that lines up with the strongly typed right here. It's a reference. So it depoints it, dereferences the pointer once to another pointer. And then that pointer type to node insert. Just put it right there. Okay.
Let's make a function that finds a node. Once you have a list, at some point you're going to want to see what's inside that list. And this function is a lot like the function we used to print out our list, but instead of printing the elements, it's just going to go through until it finds the one we're looking for.
Yeah, okay. Struct node head constant value. And then we'll do struct node temp equals head, and then while temp is not equal to null, if temp m value equals value, then printf node found at position.
And if it does, it returns a pointer to that node. If it doesn't find it, then it returns
a pointer to the node. Yeah. Yep. Turn temp.
It returns null. Now we can go back down to main, and now let's tell it to find lucky number 13. And just to make sure it works, let's print out the value of the node it returns.
Okay, so let's do TMP equals find node head 13, then printf found node with value d/n TMP and value. And
we'll compile it, and we'll run it, and look, we found number 13. And that's great. And so now, what if we didn't...
stop that. I don't think I increment
Didn't want to always...
I definitely don't increment the pointer here at all, do I? Yeah, that's gonna leave infinitely. Yep.
always
Cool.
insert at the front of the list. Say we wanted to insert a node after another node in the list. Well, we can make a function to do that too.
Yeah. Let's do this. Struct node. Oh boy. Struct node. Insert after node. Struct node. Node to insert after. Struct node. Node to insert.
And we just set the new node's next pointer to point to whatever the
Node to insert and next equals node to insert. Node to insert and next equals node to insert after and next.
previous node's next pointer points to, and then set that node's next pointer to point to the new node.
Then, yeah. Node to insert and next equals to insert after equals node to insert.
So
Insert node after, make this void.
So just to make sure this works, let's insert a new node, node 75 down here after 13.
Insert after node, TMP, create node. Yeah, let's do 73 like he does.
And we'll compile and run, and there you go. 75 now follows 13.
Yep.
Note that the order is very important here. What would happen if we had changed the pointers in the reverse order? Think through it for a minute. We would set...
If we changed it in reverse order. So node to insert him next equals node to insert after him next. Okay, hold on. Node to insert after. Node to insert after. Next. So that's the node to insert him next to. Okay, so that takes the next node and then just sets it there after. And then, okay, yeah, that makes sense. That makes sense. Okay, singly linked lists. Simple. Totally simple. Alright, well, that would just fuck the order up. Wait, no, if we didn't do that, then we would lose. We would lose the rest of the array. We would lose the rest of the linked list if we did that. That would be not
Set
good.
the pointer in the list to point to the new node. But now we've lost its next pointer.
Yep.
So when we...
I never really programmed in Java much, admittedly. Okay, well, that's a lie. Java was my first programming language back in high school. But we didn't use any of the advanced features. We just basically went to for loops, and that was it. We talked about classes, we talked about objects. So I didn't use them much, but in college we had an assignment, and I decided, all right, I'm going to use Java. I'm tired of Python, I'm going to use Java. It's actually kind of nice. It's definitely not as easy as Python, but shit. It's like C. You get sort of the maybe slightly more clunkiness of C, but you can do more. And it's a little faster than Python, I think, so. And it's strictly typed. I like that. You know, I'm going to implement this here just to see it work. And he did double pointed ahead so we can reassign it. Then struct no to delete. Okay, so we take a look and we see if the head is the node to delete. Then we set head. So, yeah, equals node to delete and next return. Do I understand what's going on here? Pointless. Yeah, this is a pointless. That is a pointless return. Oh, this is a void function. I need to look at my function headers better. Redundant function at the end of, you know what, fine. Remove that. Okay, so if the head equals node to delete, then we'll set head equal to node to remove next. That makes total sense. Okay. So now we need to find previous node in the list. This is going to be great. Equals pointer towards the head, or equals the dereference of the head. And then while temp is not equal to null, and temp at m underscore next. I don't like that. It's not equal to node to delete. Temp equals temp next. Okay, and then if temp equal to null, return. Temp and next equals node to delete. Node to delete. Node to delete. And next equals null. Null. M underscore next equals null. Oh boy. Why is this erroring? Not assign read only type. Yep, so basically that means it's just no more const.
Not Grant's iPhone. Disconnected.
I am checking messages. Okay.
And if we compile it and run it, it totally works, but it just isn't as clean as I would like, and if my list gets long, it's going to be really slow. So let's make our list doubly linked. And we're going to go up here to where we define the struct and add another pointer. I'm going to call it prev, short for previous. And now we go through our functions and handle that extra link. This is going to work differently for different functions. When we create a node, we need to initialize the link.
Okay. Here, let's see. What is he going to make it to? No pointer? Yeah, it's just going to make a null pointer.
When we insert a new node,
you insert a new node. Okay. So star head previous. Okay, well, we're inserting at head. So previous is going to be node to insert.
Then we need to make sure that the previous...
What? Oh. Yeah, okay. If node to insert. I think this happened here because of, like, I'm going to say order of operations between those two, so this needs to happen first. The dereferencing happens first before that can be grabbed.
Link now points backward.
If node to insert at m next is not equal to no pointer. I'm kind of just throwing those both. Node to insert, oh god.
Word appropriately. And down here in our remove function,
Node to insert, oh boy. Node to insert after.
previous link now points backward appropriately. And down
Okay. Yeah. Node to insert improve equals node to insert after.
Down here in our remove function, we now need to take the previous link into account. And down here in our remove function, we now need
Okay. Take the previous link into
to
account.
take the previous link into account. But
So for the head,
it's useful here as well. So now we
now I can get rid of all of this useless shit. Goodbye. Node to delete. Previous next equals node to
now
delete.
we have a link to the previous node. So now we link them up. We're going to link the previous node's next pointer to the removed node's
If node to delete.
next node. If there is a next node, we want its previous pointer to point back at the removed node's previous node. And in the case where we're deleting the head, we need to make sure that the first node's previous pointer points to null. Unless, of course, there is no first node. And then for good measure,
Okay, like that. Then you put this back here. I'm going to step through this eventually.
let's just set the removed nodes links to be null, just in case anyone gets any big ideas and thinks about trying to follow those links after we've removed the node. So let's big ideas.
This is apparently a safety thing. If the reference to head was null pointer,
And thinks about trying to follow those links after we've removed the node.
in case someone tries to follow node after deleting head.
The node gets any big ideas and thinks about trying to follow those links after we've removed
Just to follow links after deleting the
the
head.
node. So let's go down to main and see if it works. Just for good measure, I'm going to also try removing the head because I just want to make sure that part of the code works too.
Okay, so go here, print list head, free that later. So let's remove, delete node head tmp, delete node as a reference to head, and then head itself.
So let's compile it, we run it, and we segfault. Which really isn't all that surprising. I just went through and wrote a lot of code. I updated a whole lot of pointers, and it would have been miraculous if it had
I haven't taken time to actually step through and like read what's going on here, so
actually run.
because
I went through this pretty quickly.
I'm copying and pasting right now, and that is not the ideal way to learn. So I'll need to step through this and see what's going on, make sure I can logic and reason through it in my head, and that'll be good.
Those extra previous links are convenient, they make deletions fast, but they also add complexity, and apparently I didn't handle that complexity very well. So let's figure out what went wrong. Okay, so let's load it up in our debugger, and we're gonna run it, and it looks like we segfault here on line 31. And if we check our head pointer, we can see that
Let's see if I segfault on line 31. Line 40.
the head pointer is null, meaning the list is empty, but I forgot to check for that case, and I just went ahead and dereferenced the pointer anyway. So let's fix it, and we'll
Insert at head. Yep. Okay. It's exactly where I am failing as well.
compile it and rerun. And I just went ahead and dereferenced the pointer anyway. So let's fix it.
Okay. Yeah, and then it even warns you right there. It says in main though. If the pointer towards head is not equal to no pointer,
Let's fix it, and we'll compile.
then it just set the null pointer right there. Okay.
We'll compile it and
Note to insert.
rerun it, and now it works.
Okay, cool. All right, well, I am going to take some time to step through this and see what is going on. And then once I finish this, I think I'll be done with part 1 of this video, going through the introduction. It took me 2 days to do this, which is honestly kind of okay. So do the same thing for C. Get some practice with pointers to find a doubly linked list. Yep, right functions to find insert. Yeah, just to get some practice with pointers. That's exactly what I needed to do, is just to get comfortable with pointers. And I definitely went and got some pointers done. Like, for example, I'm still living at home. No job yet. Haven't really found out what I like to do with life, or with a job at least. And so I just went and sat for 2 hours in a auto repair shop waiting for my parents' 4Runners to get fixed. I never finished it, but that gave me time to go and watch some videos about pointers and such. So now I get I have a more solid understanding about the reference operator and the dereference operator. Yeah, I'm just gonna take a few steps through this and then see what happens. So what's the best way to start debugging than to just start debugging? So here we define our, well, I guess they were, I probably skipped those. So we have both of our pointers, they are set to null. I'm not even going to, I'll step through it a little bit, but I'll just skip over it eventually. And then we keep making structures here, and then they just keep pointing back to themselves. Like, yeah, that's pretty cool. So we have our head node at 404300, right? And then here it is, 404300. We can see that the imprevious is working, which is pretty cool. So I'm going to skip ahead to where all 25 of these are done. And then we have m value equals 24 right here. Beautiful. Yeah, it'll be kind of a pain to go all the way to the end of this. Yep, classic linked list. Classic linked list. Okay, so we will set TMP to find node at the value of 13. Let's step into that function, and then let's see what happens. So we have our struct node, we have our temporary node that we set it to the head, and then while we iterate through all of these values, we keep on stepping to the next one, and eventually we should reach this value right here. Yes, we do. We have found it. Temp is 13. That is what the value, that is what value is. You can see it. Yep. And then we will step out of that function, and then we check the console, found node value 13. Beautiful. And let's see this insert after node right here. So we'll step into it, and then we are going to insert. We need to, well, I guess we're going to create a new node first. That was in the function. That was in the function call, right? Yeah, that makes sense. So we create a new node using malloc, which I am getting used to, but it doesn't really seem all that bad. You just grab memory from the heap, and then it works. And then size of just makes it so easy. Size of makes it so easy, I guess. And it's relatively simple function call too. You can look at any Python library, and it's like you have 10 million different parameters you can pass to, like, oh, information overload. Size. Give it the size. That's so nice. That's honestly really nice. So, we'd set the value to 73. Creating this node, we return it, and then next, that's unfortunate. Should have gone to step in, so I am just going to stop this and then rerun it because I want to see what's going on. Never mind, I totally forgot to do that, so do that, and then we'll step into this one, step into, continue, step into, there we go. So we now have the node to insert right here, and it has no, its mNext and mPrevious don't have anything inside of it, so we will step over, and then we'll see that mNext is set to the node to insert mNext. So I wish I could get a visual representation of this. That would be helpful. That would be very helpful. I'm looking this up. Pedagogically. Pedagogically. Okay, cool. Hold on, can I have it say it again?
Pedagogically.
There you go, beautiful. Pedagogically. But here we are. Okay, so now it checks to see if the node to insert mNext, if the node to insert mNext is not equal to null, then it will do whatever the next step is, which it'll take the node to insert, it'll go to mNext, and then it'll go to mPrevious, and then it'll set that to be the node to insert after. Okay, so let's step over, see what happens. Okay. And then I'm still not wrapping my head around this all too well. So the node to insert, I'm going to set the node to insert the next one, the next head. Okay, so we have the next head, right? And the next head, the next previous one is going to be the node to insert after node. Insert after node. We have the node to insert. I might need to draw, I might need to get paint down for this. So we have node here, 0, 1, 2, 3, 0, 1, 2, 3. And so right now, these are the ones that are linked together. These are the ones linked together. And then let's say we want to insert right here. Okay, so we'll make this node 73. So then we will set this is the insert, so insert, set node to insert mNext, node to insert mNext is going to be the node to insert after mNext, so that gets set there. Boom. Step 1 done. Right, and the node to insert, if the node to insert mNext is not null, which in this case it's not, then the node to insert mNext, and then the mPrevious, the node to insert mNext, mPrevious, so whatever is going to point in that direction, it's set to node to insert after, so that gets set back. And then, therefore, now this connection is one way, and there needs to be more rearranging done. So, the node to insert at mPrevious is now nothing. Okay, hold on. Node to insert at mPrevious is nothing. Is nothing. So that needs to be set to node to insert after in that direction. And then the node to insert after mNext will then be set up here, severing. Where's the erase? This is probably it. Severing this connection entirely. And now we have successfully inserted a node, and we can move on. Okay, I'm not going to worry about doing that. Now, this is one thing that confused me, so let's step into it. And then we don't have to worry about the head step right now. I'll go through that in a little bit. So we will step over through this if statement. So let's say we want to delete this node 73 now. So let's see what happens. Follow through this visually. Node to delete at mPrevious, mNext. So the pointer, so this connection right here is going to be set to the node to delete mNext. So node to delete mPrevious mNext is then going to get set to this, which in the process, so mPrevious mNext will then sever this connection right here, so that is no more. And then we will check to see, step over, we'll check to see if the node to delete mNext is a null pointer. So if it's not, in this case, this is valid, we will step over and we will do we will run node to delete mNext mPrevious now runs to here. mNext mPrevious now runs to there, severing this connection entirely. I wonder if this is a memory leak. I'm going to run this through Valgrind after this and see what happens. So we step over, boom, mNext and mPrevious are now both severed, and now we kind of just have this sitting here freely. Freely in memory. So I think that's going to leak. I think that's just going to leak. Anyway, for now, let's keep going. Step over, and then we'll step into this, and then this is the head. So it'll see that head is equal to the node to delete. And then we will step into that, and then we will set the node to delete at mNext. We'll just move the head over. So this sets the head directly to here now. So this, I'm going to mark this. This is now the head for thinking about theory and computer science graphs. So now we'll step over, and then if head is equal to null pointer, yeah, if head is equal to null pointer, which it's not in this case, then we're good. And then the node to delete will have all of its connections severed again. I probably should have had that open while I was doing that, and then free the temp variable, and then we should be good to go. I'm going to run this through Valgrind to see what happens, because I really think there's a memory leak in here. And luckily, we have clocks, we have that. We have main.c built up right there. So, nice. Let's see what happens if I go in here. In my program history, I should have Valgrind. I definitely was doing a little bit of, I definitely went and downloaded some C books last night, let's just say. Okay, I don't have Valgrind. You get to see my file system. Yay! File system. Oh well. Valgrind. How to use Valgrind. Totally forgot how to use it. So it's just going to be like 2 functions. So Valgrind, leak check equals full, and then we're going to do cmake builds clocks. Valgrind. Yeah. Okay, definitely lost 428 bytes, and then I guess I don't free anything else up, so I wonder, how am I going to malloc and create nodes? 2 bytes are definitely lost here. Let's see. If I get rid of this, build it, and then go and run it, does that only lose 1 byte? No. Okay, yeah. I just don't delete the, I just don't free anything up after this. So, that's a problem. Yeah, plenty of memory leaks right here. So, let's see. What happens if I do a void and then free? Yeah, let's just free list. And then we will set the temp node to point at it. Then yeah, let's see what happens. So we set struct node, and then we just have it write it for us. Yeah, that's not, yeah, this is not very good, this is not very good. This is not very good. So, let's see. Let's go to while temp and next is not null pointer. We can free temp and then set temp equal to, here, we'll grab the struct node next ptr equals temp mnext. This is going to be a little bit sketchy, but that'll be okay. Void free list. Okay, I gotta launch this through in my head again. All right, so we'll set temp equal to head. So I can't use it after I free it, so that's the issue. So we'll do we'll make another one. Another struct node temp next equals whatever temp is, mnext. Okay, and then we'll do while temp next is not equal to null pointer. What is it throwing? Next can be made into a pointer constant, can it? We'll see if it throws a linting error even after this. So now, let's do while temp next is not equal to null pointer. Let's free temp. No, that's not going to work. Reference? I don't think that's going to work either. So we need to free. Let me think about this. So we have a pointer to the head. We need to free whatever is inside of it. So I think it's okay to free. Is double free an error? Double free error in C. Leads to undefined behavior. That sucks. Okay, so in this case, I know that. So here, yeah, we gotta add an edge case. If temp equals null pointer, then we can just return. All right, so now we know it has something inside of it. So if it has something, then we will set a temporary node, the temp next, and then maybe I am thinking about this too hard. Struct node $temp equals $head, dereference, asterisk, head. Then we'll see if it's a null pointer. If it is, then we'll just return it, and then we'll grab the next. We'll grab next. So if temp next is, if it exists, well, I guess I do have previous. I do have access to previous nodes. So I could theoretically go while temp is not equal to null pointer. Yeah, if I know I'll be at the end if I'm at temp. Ooh, this is a tough problem. This is a very tough problem. Okay, so if temp is equal to null pointer, then we will return. So then while the temp is not at a null pointer, we should do struct temp next, struct node star temp next equals temp m underscore next, and then we will free temp, and then we will set temp equal to temp next, and then that will keep on going until it reaches null pointer. And then we'll do, I don't think I want to do this. Free list, make that a reference to the head. Okay. Let's see, will it run? It does run. Cool. Now let's see. What happens if I do this? Okay, hey. Only 24 bytes lost this time. 27 allocations, 26 frees. What happens if I do this? Is that going to error? Find out, won't we? Find out. What's it gonna be? Yes, dude. Oh. All right, cool. This documentary fix memory leaks. Cool. This little YouTube documentary of my process in learning basic linked list stuff. It's worked. This just worked. Like, I actually just wrote this code from scratch, and it totally works. And I'm happy. I'm gonna go take a shower and probably edit this together.